Good evening, and thanks for coming back for the second installment in this series on average atomic mass. In this particular one, we're going to consider the reverse of the problem in the first screencast. We're going to use the average atomic mass to calculate unknown percent abundances of isotopes. We're going to be using the same generic equation that we used before, where the average atomic mass is equal to the summation of the mass times the percent of each isotope. But all the problems that you will see on the assessment of this flavor will be limited to just two isotopes. So 2 mass times percent abundance terms. So let's look at a couple examples. In this first example, we're going to examine boron, which has an average atomic mass of 10.811, which comes from two isotopes, 10B and 11B. And there's their respective masses. So I'm going to go ahead and set up my equation where the average atomic mass, 10.811, equals the mass of the first isotope times its percent, and I'm just going to let 10B represent the percent of that isotope, plus the mass of the second isotope times its percent. Now this is one equation with two unknowns, 10B and 11B, so we know that we're going to need to set up a system of equations. But since there are only two isotopes, we know that the percent of 10B plus the percent of 11B is going to equal 100%. I want to write that in decimal fashion, so I'm just going to say 1 equals 10B plus the percent that's 11B. And we're going to use solving by substitution to solve this. So I'm going to take this second equation here, and I'm going to solve that for 10B by subtracting 11B from both sides. You could solve for 11B also. I, as a habit, always solve for the smaller of the two isotopes because it keeps everything in my algebra steps positive the whole way. If you solve for the larger of the two isotopes, it doesn't matter, but you'll end up with negatives through the middle of your steps, and then those two negatives will cancel out at the end to get you a positive answer. So just out of habit, I always solve for the smaller of the two isotopes. So with that done, we can go ahead and plug in 1 minus 11B for every time that we see 10B in the original equation. Okay, with that done, we now have one equation and one unknown, so we're good to go. And at this point, it's just a series of algebra cleanup. So the first thing that I'm going to do is distribute this mass to both of these terms. Okay, so now we can see that. And now it's time to start collecting terms. I have minus 10.01293811B and plus 11.08930511B. So I'm going to go ahead and collect those two terms. So my equation now will look like this. And now I can move this numerical term over to the other side by subtracting it on both sides, and I get this. Now all I have to do is divide both sides by 0.996367, and that gives me 0.80097 equals 11b, or 80.097%. So if boron is 80.097% 11b, that means 100 minus that is going to be 10b, so 19.093% is 10b. And we're finished with that problem. Let's do one more example since the algebra on this is kind of long and tedious. So now we're going to do another example where I've provided you with the average atomic mass and the mass of two isotopes. So I want to set this up just like before with the average atomic mass equaling the mass of each isotope times its percent. And now for the second equation in our system. And like normal, I'm going to solve that for the smaller of the two isotopes. And now I'm going to plug that in. And distribute. Now I'm going to collect my two 37Cl terms. Now I'm going to subtract this from both sides. Divide both sides by this. Convert to a percent. And solve my other percent by doing 100 minus the first percent. Okay, I hope this helps you guys get through this kind of long and tedious algebra, and we will see you back in part 3 for nuclear bonding energy.